Okay, so in this video we're going to talk about minimum spanning trees and maximum spanning trees, but in general just spanning trees. Okay, so we talked about what a spanning tree was in the last video. It's when you have a network like this one here. Doesn't even have to be a weighted network, but we have a weighted network here. It's when you have a network that's not a tree already. So this isn't a tree because it has circuits, has a lot of different circuits in it. Well, to redraw this, I don't want to say redraw, but to take this network that has circuits in it and turn it into a network that's a tree, if you can do that, turn it into a network that's a tree, then it's a spanning tree. In other words, it's a tree that still actually visits every vertex of the network. So what we want to talk about now is just different ways to make this into a tree, but there's two things that are sort of involved. Either we want to find, depending on what our goal is, we want to find a minimum. It's minimum spanning tree, minimum spanning tree. Why would we want to find a minimum spanning tree? Well, it depends on what this situation, what this weighted network represents, what these numbers represent. Now, this network that I drew is based on a network, an example they give in the PowerPoint. Let's say all of these edges are roads, okay? And they want to lay power lines. You know, sometimes power lines are wires, but sometimes they're cables in the ground. So in this example, they're digging cables in the ground, and they're laying cable. Each of these vertices represents a city in the Amazon jungle, actually, according to the example. I don't know if this is a true example or what. So these are all cities in the Amazon. I don't know if the Amazon forest or just the Amazon River basin, whatever. In the forest, let's say. I think there are some cities in the Amazon forest. So obviously it's kind of hard to work there because there's so many trees and stuff. That's why they have to lay the cable alongside where there's a road already. It's too hard to try to make a new road or dirt roads through the jungle to lay cable. So they're just laying the cable alongside roads that are already built. Okay. Well, what does that have to do with anything? What's the big deal? Well, these numbers, maybe they represent how many thousands of dollars every mile, or let's say I want to be realistic. I don't know what they say in the example they give. But let's say it's in millions of dollars. To lay the cable from G to F, it costs $42 million. To lay the cable from F to E, it costs $62 million. So you don't need all of these cables. So like I said, these are roads. You want to lay cable that connects all of the cities, but you don't need any redundancy. Like for B to have cable going to it, so it has, I don't know if these are power cables, let's say they're power cables. For B to have power, you'd only need one of these things going to it, okay? So if you could get rid of this one and this one, or this one and that one, it might only cost $45 million instead of $151 million if you had all three of those going in there. So you're trying to save money, okay? So that would be a reason why you want to make a minimum spanning tree, to save money. Why would you want to make a MaxST? Well, or a maximum spanning tree? Well, these numbers might represent, let's say, if the cable being laid was for phones. Okay, and these numbers represent how much money they would make, the phone company would make, by having these different connections. So this 64 doesn't mean that they would have to spend $64 million. It means they'll make $64 million. So if that's what the model represented, you'd want to make a maximum spanning tree. If you're trying to go from the standpoint that this is a cost where you have to pay out, then you'd want to make a minimum spanning tree. Now, I don't believe we're going to actually talk about how to do that right now, how to make a minimum or a maximum spanning tree. That's in the next section. I could do it right now, but I want to give you time to think about just how to make a tree first. So remember, this network has a certain amount of redundancy, so there's a certain amount of trees you could make out of it. Alright, so erase this. So in other words, there's more than one tree. Also, it can be the case, we're not going to actually talk about minimizing and maximizing the tree yet, but it could also be the case that there's more than one minimum spanning tree and more than one maximum spanning tree. In other words, different trees could have the same weight, and a tree with like a weight of 200 there could be another tree with the same weight, and let's say that's the minimum. So there can be more than one answer to minimum and maximum spanning tree, but let's just find what the redundancy is. So we have how many edges? 1, 2, 3. It'd be really good for me to label these, but I don't want to, I don't know where to write it, so I won't be confused. I guess I could write it in a different color. I want to make sure I have all the edges labeled, just so I know how many there are. Okay, do I have all of them labeled? Looks like I do. So it looks like there's 12 edges. How many vertices are there? A, B, C, E, 4, 5, 6, 7. Is there 7? 1, 2, 3, 4, 5, 6, 7. So there's a lot of redundancy in this network. In other words, we can get rid of 6 edges. That's what this means. It means there's 6 edges there that really don't need to be there for it to, you can still have it be a network. So let's erase 6 edges. Now it can't just be any 6 edges. You have to make sure that everything stays connected. But I'm going to erase this edge just because it has, this is what you're going to start doing when you're trying to find a minimum spanning network. Get rid of an edge that had the, I believe that, well, this one actually has the most weight, but that one had a high weight too. We can get rid of this one too though. You can see that everything's still connected. Basically, you can go ahead and erase an edge, just in general. Now, you're going to hopefully do enough of these examples so you see what you can do. But you can erase an edge whenever you notice that by erasing that edge, there's still a network. Like I can erase this edge too. Everything's still connected. So I've erased 3 edges. I should be able to erase 3 more. I can erase this edge. Everything's still connected. And like, you can erase any 2 of these. So I'll erase the 2 bigger ones. This actually might be a minimum spanning tree that I just made. Okay. We didn't use it. There's an algorithm that we're going to talk about in the next section that will tell you how to go about finding a minimum and a maximum, actually, spanning tree. But I didn't use it. I just used common sense. I just erased like some of the ones that had the biggest weight. This probably is a minimum spanning tree. It's pretty close to the best spanning tree as far as minimizing the cost. So, and you would do it reverse if you wanted a max. Like whatever the numbers were, you could start getting rid of the smaller ones first, the ones with the least weight. But like I said, we're going to specifically talk about how to do that in the next section. We're not going to talk about it right now. So make sure you come to office hours if you have any questions. Keep up with the homework. A lot of people aren't. Some people are. So good on that. But yeah, come to office hours. Keep up with the homework. There will probably be a quiz coming up later this week, and there will probably only be 1 quiz actually. And then I'll try to make some announcements about the final exam this week that hopefully will be good announcements, I hope. It depends on I have to see how many people have done the homework and what everybody's average is, but there's a pretty good chance that if you don't want to take the final exam, I can make it optional, but then your grade will just be what it is after you get done with the homework. But if you've missed the test, you should probably, there's a couple people that missed an exam, you should probably take the final. And well, if you have any questions about that, I'll probably email those people specifically anyway, but you can always email me first.